All right, next up we have Dean Denton, who's going to talk about the origin of the Pluto-Charon binary.
Thank you so much, Simon, and thank you so much for inviting me to be here. 10 years ago, I was an intern at the Lunar and Planetary Lab during the flyby and was so taken by the images of Pluto, like everybody else, that I really wanted to be a part of studying Pluto. So it's very exciting to come full circle and actually be a part of studying Pluto. So thank you all for having me be here. Now, we've talked quite a lot already about what happens when two similarly mass objects collide. Let's go ahead and talk about it. So I'm going to talk about the origin of the Pluto and Charon binary, and it'd be cool if my slides were here, but instead I'll have to do this sometimes. So there are two relatively unusual things about the Pluto and Charon system that are of note and which have guided people in their understanding of how the system formed. And the first is that Charon is, as we've noticed all week, unusually large and thus very interesting. But the other thing is that the system has an unusually large amount of angular momentum. And because of these two things combined, there's another system that also has both of these things, and that is the Earth-Moon system. Here it is. And the prevailing theory is that the Pluto and Charon system formed similar to how the Earth got its moon, which would be through a giant impact. Thank you so much. That's so helpful. But let's talk about what makes the Pluto-Charon collision unique relative to the Earth-Moon system. So the moon-forming impact is what forms the foundation of our understanding of satellite capture when it comes to a giant collision. But satellite capture may operate differently across the solar system. When we use the moon and the Earth as our lens for trying to understand how every collision-based satellite system gets its satellites, we might be missing a few things. And part of this relates to how the physics changes when you scale down from the size of Theia hitting the Earth to a proto-Charon hitting a proto-Pluto. So if this video works, beautiful. It does not. If this video did work, it is one of Jacob Kekeris's simulations of the moon-forming impact. And what happens in the moon-forming impact is that a large Mars-sized body called Theia will come in and collide with the Earth. Both of them are assumed to lack strength, which means they behave like fluids. Because they behave like fluids, what happens is Theia comes in, collides with the Earth, and then the exchange of energy between the two is largely contained in the massive deformation of both bodies. So both bodies experience massive shearing on a global scale, which ultimately largely destroys Theia and produces a debris disk from which the moon will eventually form. That's what happens in this video. It's really cool. You should look it up on YouTube. So the main takeaway from that description is that in the Earth-Moon collision, we can assume that both the Earth and the moon will behave like fluids. And the reason we can do this is because the collision is relatively intense. And the reason the collision is relatively intense is because the speed at which two bodies collide when they are similar in mass is dictated by their mutual gravitational attraction. So because the Earth and Theia, which will become, remnants of which will become the moon, are relatively large, they collide very fast, which should produce widespread melting and vaporization. So when we approximate them as fluids, that is kind of okay to do. Maybe. But the thing is, that may not be true when we get to Pluto. And the reason for this is that Pluto is small. It's about 17% the mass of the moon. And in studies of giant impacts between bodies in the early solar system, looking at asteroids up through super-Earths, recent studies have shown that material strength is important for bodies that are the size of Pluto and smaller. Actually, they're important for slightly larger bodies as well, but that's not what this talk is about. But the problem is, we know that material strength is important, but the effects of material strength on collisional outcomes is complicated. So it's not entirely clear just from knowing that we need to add strength what will actually happen during and after the Pluto-Charon impact. The nice thing about the Pluto-Charon system is that we have New Horizons, which was able to give us much more information about Pluto and Charon than for any other large Kuiper Belt binary. So we went from the Hubble Space Telescope images to what we now have. And by revealing Pluto's surface, that allows us to make inferences about its interior and evolutionary history, something that we've been doing all week. But for the purposes of going backwards to the giant impact, we now have more information about Pluto and Charon than we do about anybody else, and that allows us to make much more detailed guesses about what's going on. So when we're trying to derive the origins of Pluto and Charon, we can begin with this improved understanding of their thermal and structural state today and work backwards from there. And the reason this is of interest for the Kuiper Belt writ large, which is what I've been kind of alluding to, is that many of the largest Kuiper Belt objects have large mass fraction satellites. And we talked about this a lot on Wednesday. These systems are so interesting. Pluto and Charon are not alone. We have Eris and Dysnomia, Makemake, and its moon. I will not list them all. They're all great. And it raises the question, why do all of these bodies have one or more relatively large mass fraction moons? And are they all getting those moons through the same process? Are all of these happening through collisions? And if so, what has to be happening in that collision such that it's a likely outcome for a collision in the early Kuiper Belt? Because we know the most about Pluto and Charon, if we analyze what happened in that system, we can learn a lot more and try to reconstruct what's going on, not just for the Pluto-Charon system, but for all of these other systems as well. So some of the major unknowns in Pluto's interior that are relevant to this particular side of exploring Pluto's origin are, first, does Pluto have an ocean, and did it have one at the time of impact? This has been discussed somewhat in terms of whether Pluto starts hot or cold, and I'll get back to that later in the talk. One thing that's also of interest is the core active? And by active, I mean hydrothermally active. Does serpentinization of Pluto's core occur, and when does it occur, and what about Pluto causes it to occur, whether it's an amount of heating at the start or later events? And what is the thermal structure of the ice shell, and how big is it also? All of these things are pretty fundamental unknowns about Pluto that we're still trying to reconstruct. And I can't answer all of these questions, but because all of them relate to the initial formation of Pluto and Charon, this is something that we have in mind when we do these simulations of the Pluto-Charon collision, and these are outcomes that we're trying to think about when we analyze the results. Now, on the Charon side of things, there are also major unknowns about its interior that were discussed on Tuesday afternoon. And one of the biggest is what is its interior actually made out of? We could assume that it's about 50% rock, 50% ice, but there are huge error bars in that number. And the major questions when it comes to the outcomes of the Pluto-Charon collision are two. The first is, does Charon have an ocean early on? What causes it to form that ocean, and how long does it keep it? And then, how destructive was the initial Pluto-Charon impact? Does Charon lose material during that impact, and how much? And this was alluded to during the question session of the last talk, but either Charon could lose a lot of its initial mass such that the final body is very different from the initial body that hits Pluto, or it doesn't. And those both have implications for its geologic evolution and the evolution of the system. Now I want to talk a little bit about why giant impacts are very useful. And the reason giant impacts are very useful at answering the questions that I just laid out for both Pluto and Charon is because the outcomes of giant impacts, including whether Charon gets captured as a satellite at all, reflects the composition and the internal structure of both bodies prior to their collision. When we add in material strength, that means that how much ice and rock Pluto and Charon have prior to the collision will affect the outcome. And because of that, we can use giant impacts as a really useful tool to inform our understanding of both thermal and mechanical variations in Pluto's interior. I'm going to start by covering the mechanical aspects, but I will get to the thermal aspects and how hot Pluto and Charon are prior to impact later in this talk. So let's talk about the history of the Pluto-Charon impact in terms of how we've been studying it. And I want to talk a little bit about what I mean when I say material strength, because if this is not intuitive to you, it may seem a little confusing. So previous simulations of the Pluto-Charon impact neglected material strength. And like with the moon, what that means is they assume that both Pluto and Charon behave like fluids. They do not have strength, they do not resist deformation, and that dictates how the collision operates. So these are a series of timestamps from a simulation that was done by Robin Knupp in 2011. Robin did the first simulations of the Pluto-Charon impact in 2005 and then followed up in 2011 because she was looking at whether or not the Pluto-Charon impact can also make the moons. Other simulations were done also in 2019 by Shoto Arakawa and his team, and they had similar results to what Robin produced, so I'm showing you Robin's figures here. What's important to note about what's going on here is, so the initial impact is in the top left, and what you'll note here is that the body so this body here is Pluto. This body here is Proto-Charon. What you'll note is that it's very big, and the reason why it's very big is because it then proceeds to lose a bunch of its mass during the impact. What happens during the impact is that in these subsequent panels, the transfer of energy from the collision occurs similarly to what I described for the Earth-Moon collision. Both bodies experience massive deformation, so Pluto and Charon massively deform, and Charon in particular, because it is smaller in mass, experiences whole body shearing, which then causes it to lose a bunch of material to debris, such that the initial Charon that you start out with, which is this really big impactor, and the final Charon that you gain at the end is a lot smaller. Though I will say there is a change in scale between these two figures, so it's hard to tell, but this Charon is smaller. So what you end up with is Pluto, a smaller Charon than you started out with, and a debris disk. The other thing that's important here to note, which may not seem that important to people that aren't impact modelers, but is very much of interest in terms of what's likely to happen in the solar system, is the impact angle. Pluto and Charon are colliding at a relatively oblique angle, which may be hard to tell, but if you look at this figure, what's happening in the first panel is Charon is essentially grazing Pluto at around 70 to 71 degrees. We consider this a grazing impact, where if 0 is head-on and 90 is a fully grazing impact, Charon here is hitting Pluto at around 70 degrees. And the reason it's doing that is because both bodies lack strength. So Charon has to graze Pluto just enough to then get caught, shear, and then snap away from Pluto and be gravitationally bound to the system. If the impact angle is less, if this impact is not oblique, what happens, and I can show you this in the next slide, is that the two bodies will merge because they lack material strength. So the requirements of previous simulations to produce the Pluto-Charon system are that Charon has to start out really big, it then has to lose a bunch of material to debris, and the impact angle has to be relatively oblique. The reason the oblique impact angle is a concern is primarily because oblique impacts are slightly less likely to occur in solar system history. The average impact angle at which things collide is thought to be 45. So the problem is, like I mentioned before, at the size of Pluto and Charon, strength influences impact outcomes. So when we look at the outcomes of these simulations in which the absence of strength clearly dictates how the satellite is captured, we must now then ask what's going to happen when we add strength. But let me provide a demonstration of what happens when two bodies the size of this size collide without strength, but it's at 45, the average impact angle. So they will briefly separate, but then merge into a large egg-shaped body. And this is obviously not what happened because Pluto is not Haumea. But this is what I mean when I say when two bodies lack strength, they deform at a global scale and at lower impact angles rapidly merge. So let me get back to the key question, which is how does strength change whether Pluto retains a satellite after a giant collision? And what I mean by strength is what we're going to do is assume that both Pluto and Charon, being made of rock and ice, will deform like rock and ice do under intense temperatures and pressures, instead of just assuming that they both behave like fluids. How does that change this outcome? And what does that mean for the conditions of the collision itself? So now I must tell you about how giant impact simulations work a little bit. This is a schematic diagram of what a giant impact simulation looks like. And when I say giant impact simulation, I'm using a version of a smooth particle hydrodynamic simulation, or SPH simulation. These were initially designed to look at collisions between galaxies, and what a lot of planetary scientists have done is take those types of codes and shrink them down to look at collisions between planets. So here on the left, I have Proto-Pluto, and on the right, I have Proto-Charon. And what I did to start thinking about how material strength changes this collision is to start from the same sort of initial parameters that Robin used in her 2005 and 2011 papers. So what she did is she assumed that both of these bodies have a constant interior structure. So both Pluto and Charon are assumed to be 85% rock, 15% ice. If you don't like that, me too, that's fine. I don't necessarily believe that, but when we test whether material strength matters, we should start from known results and then work from there. So we will start by assuming that both of these bodies are largely rock with some ice, and that we have big Charon that I showed you in the previous slide. So Charon here is assumed to be 1/3 the total mass of the system. So that is large. What we then did with that initial framework is test a range of impact angles and impact velocities. So we tested impact angles from more nominal, so that clustering around 45. So we tested between 40 to 55 would be considered close to the nominal 45-degree case. And then we tested more oblique angles up to 70, which is close to what was used in previous work and what was necessary to capture Charon around Pluto. And then we also tested a range of impact velocities, which in the Kuiper belt tend to be slow. And this quantitative scheme here, the impact speed, this is the ratio of the impact speed to the escape velocity of the system. And what this actually works out to in kilometers per second is around 1 to 2 kilometers per second. These impacts are not very fast. And the reason they're not very fast is because unlike the Earth and the Moon, Pluto and Charon are much less massive. So their mutual gravitational attraction is going to cause them to collide at much slower speeds. So the collision is a lot slower and will also be a lot less destructive. Now, the new things that we're doing here that previous work has not done. The first is varying spin on the target. So I'm changing the rate at which Pluto is spinning prior to the impact. And I'm doing that by starting with a Pluto that is not spinning at all and is then just hit by Charon, and increasing that spin rate from 10 hours to 6 hours to 3 hours to see how this affects the impact outcome. And what we'll see is that it does. But the other thing that we're doing is looking at material strength. And what that means is we had to take the SPH code, which is again designed to simulate collisions between much larger astronomical bodies where you can neglect strength, and then add a strength module onto it that incorporates friction, plastic deformation, and thermal yielding. And we did this based on what impact codes for much smaller impacts have done, such as ISAIL and CTH. And if you have questions about the strength model, I'm happy to talk about it, but I think we should get to some cool videos. So the main takeaway before I even show you a video is that simulating Pluto and Charon as bodies with material strength does produce a satellite, but how that process works changes drastically in ways that I think are really interesting, both for Pluto and Charon and for the Kuiper belt as a whole. The video didn't autoplay, that's great news. Okay. I didn't want the video to autoplay because I want to explain to you what it is you're seeing. No, don't play it! Okay. I was happy that the video didn't autoplay, but then it was played anyway. Okay, so I put in the Tokyo Drift music because it's Vin Diesel's birthday today. So I love Fast and Furious. It's also my birthday, so I feel like, thank you. Thank you. I've always wanted to talk for 45 uninterrupted minutes on my birthday, so this works out great. Thank you all so much for being here. Yeah. Anyway, I'll play the video with the fun sound will happen, but before it gets played, let me tell you about what you're going to see. And I will then play the video twice, and once without the fun music so that we can actually look at it. So this is what's going to happen. This is Pluto. This is Proto-Pluto. So the colors here correspond to the material variations. So I've colored Pluto such that the ice shell is in yellow and the core is in blue. So the blue is the rocky core. And Charon is going to enter from the top right, and Charon's ice shell is going to be in green, and its core is going to be in purple. Now the collisions, the conditions for this collision are also important to be thinking about. And the conditions are, I'm colliding Pluto and Charon at 45 degrees, and that's the nominal impact angle of the solar system. This is the assumed most likely scenario. They're colliding at 1.1 via escape, which is relatively slow. Could be slower, could be faster, kind of in the middle. Pluto is spinning at 3 hours. That's pretty fast. So something to think about. And I'm going to show you the video. We are calling this new regime the kiss and capture because of how Pluto and Karen behave during this collision. And James Keen showed you this video at the start of the week, but this is a great refresher of what it looks like, and then I'm going to walk us through what's actually going on. So a return to Tokyo Drift. So let's watch this again and I will talk us through it. What you saw there is that Karen collided with Pluto and then they stuck together and then they eventually separated to become a satellite. But what happens is they collide, Karen kind of gets away from Pluto, then they get stuck together and then they co-rotate. This is them co-rotating. And then Karen eventually starts to separate from Pluto. And they then co-rotate very close together. But Karen is stable as an independent satellite. And though it's difficult to tell in the video, its orbit is slowly starting to expand. And that's something that we can look at too. But if we step through this in a little bit more detail, the first thing that's of note is that in the first impact itself, the initial collision, Pluto and Karen collide, but they do not merge. In that video without strength that I showed you, which is at this same impact angle with these same parameters, Pluto and Karen collided, and then they eventually became one large egg-shaped body. Here, what happens is because Pluto and Karen have material strength, what that means is Pluto resists deformation. Karen collides with Pluto, but does not successfully fully penetrate Pluto to merge with it. What that means is Pluto and Karen retain their structural integrity during that initial collision, and that's what allows them to then co-rotate as one body. This is them co-rotating together. What you'll note is that Karen is draining some of its ice off of its back. This is because Pluto and Karen are spinning very fast because the initial rotation of Pluto is 3 hours. Where does that debris go? It forms a large debris disk around the system. There's not actually that much mass lost from Karen. The mass lost from Karen here is, depending on the simulation, between 1 to 5% of its mass, becomes a debris disk that is then mostly bound to the system. But the other thing that's of note here is in this screenshot, Karen and Pluto are already starting to separate. And the reason that they're already starting to separate is because when Karen collides with Pluto, if Pluto is spinning as rapidly as it's spinning here at 3 hours, what happens is they merge, but because Karen doesn't penetrate deep enough into Pluto, it's outside their co-rotation radius. So Pluto spins faster than Karen can spin with it. So it ends up lagging behind Pluto while they co-rotate together. Because of this, this induces a torque that then allows Pluto to effectively push Karen back off, at which point Karen then starts to separate and establish itself as an independent satellite that then migrates outward. So this is the initial separation. And from here, it will then migrate outward over timescales that are longer than what we can actually look at in an SPH simulation. But it is worth looking at what some of the orbital parameters are doing here. So as I just mentioned, after the initial merger, these bodies take about 10 hours to separate. So what we're looking at here is, on the x-axis, this is time in hours from the initial collision. So the collision happens here at time 0. And this distance is distance away from Pluto. So in red is Karen's semi-major axis, in cyan is its periapsis, and the co-rotation radius is that gold dashed line. And what you'll note here is that you have this very chaotic time when there's an initial merger and it's difficult to determine what a semi-major axis or periapsis might be when you are two bodies stuck together. But this is the separation, at which point Karen fully separates and then slowly starts to expand, and then its orbit stabilizes. So the semi-major axis is gradually expanding over time. These peaks and valleys in the periapsis are because Karen is so close to Pluto that it is, the actual orbit isn't quite circular and it is moving towards Pluto and away from Pluto. But it does stabilize into this tight, relatively low eccentricity orbit. This is the eccentricity that I'm showing you here. So again, this is the collision. So you drop the eccentricity down. This is when they are stuck together, and then this is the separation, at which point Karen stabilizes as it starts to slowly expand. And I'm describing this as relatively low eccentricity, even though it is not technically low eccentricity compared to, say, regular eccentricity of a moon of a giant planet. But in comparison to the previous simulations, which I showed you from Canup, which, because Karen collided with Pluto in such an oblique angle in those models, the Karen that resulted out of it was on a relatively eccentric orbit, which then needed to circularize. In this case, Karen separates from Pluto and is close to circularizing its orbit already. And the last thing to check when we're thinking about does this actually reproduce the Pluto-Karen system is going back to the large amount of angular momentum that the Pluto-Karen system has today and trying to determine, does this have a good fit? So what we found is, yes, it does. On the bottom here are the three major components of the angular momentum of the Pluto-Karen system, which are contained in the spin of Pluto, the spin of Karen, and Karen's orbit around Pluto. And all of those combine to the cyan line. And all of this is normalized to the Pluto-Karen system today. So what we want is for the cyan line to be 1. And once Pluto and Karen separate from each other, it does drop down to close to 1. So this is one of the reasons why we think this is a decent approximation for the Pluto-Karen system. Now, the main takeaway here is that giant impacts with material strength can reproduce Pluto and Karen, and I've only shown you one impact here as a kind of best case scenario. But what we found is that we can reproduce Pluto and Karen for a range of impact angles from 40 to 60, so all around the general spectrum of 45 degrees, and a range of impact velocities from very slow to relatively rapid. And this image in the back here is a zoomed out version of the Pluto-Karen system. This is Pluto, this is Karen during separation. And that big disk that you're seeing there is the debris disk that I was talking about before. And we're excited about this because the repeatability over a broad range of impact parameters indicates that kiss and capture may be a feasible origin for Pluto and Karen, because we didn't just make this happen one time, we made it about 14 times. And we feel pretty reliably sure that this is a physical process that happens at this size range when two bodies made of rock and ice collide. Now, I want to talk a little bit about what happens with respect to the timeline of when Pluto and Karen form, because kiss and capture also has implications for the thermal evolution of both bodies, both prior to and after the collision. This has been mentioned several times over the course of the week, but there have been two options that have been suggested for Pluto's early interior, and this is from Carver's paper in 2020. And those two options are either Pluto and Karen form relatively late, when you don't have aluminum 26 and other early volatile, early radiogenic elements to help you heat up. And in that scenario, you then build up this thin ocean over geologic time, and you have global compression. So we don't like this from a geologic perspective because we don't see global compression. And you can have a hot start where you form early and you form hot, and then you can sustain a thick ocean over geologic time, but then Pluto itself has to form very early and very fast. And one of the things that we can look at in our collisions is how does the thermal structure of Pluto and Karen prior to impact affect kiss and capture and whether Karen becomes a satellite. And what we found is that it does matter, which is interesting and has some potential implications that we're still thinking through. What we found is that if Pluto and Karen are relatively cold, and what I mean by cold, when we say cold, we're defining it relative to the melting point of water. So if the basal temperature of Pluto's ice shell, so the temperature at the core mantle boundary, is around 200 Kelvin, so far below the melting point of water, we end up with a very nice Pluto-Karen system. If we then raise the temperature such that the basal temperature of the ice shell at the core mantle boundary is 235, so we're getting close to subsolidus, then it gets a little bit messier. You end up with a little bit more debris, but you still produce the Pluto-Karen system. If Pluto has an ocean prior to impact, this does not work anymore. We cannot capture Karen as a satellite, and the reason for this goes back to the physics of how material strength works. If Pluto is partially molten, then it is much, much weaker than if it is entirely solid. So in that situation, what happens is Karen collides with Pluto, and Pluto cannot resist deformation because in addition to having warmer, weaker ice, It also has a liquid layer. So Charon is able to collide with Pluto and then partially merge, and then it gets stuck together in this weird snowman, super Arakoth looking thing, which is not what happened. So these results suggest that if Pluto had a hot start with an ocean prior to the collision, then what you have at the time would be this thinned and weakened ice shell overlying an ocean, which may make kiss and capture very difficult. Not impossible, but we could not do it using our traditional parameter suite. But if Pluto's ice shell is marginally subsolidus, then kiss and capture is feasible. And while Pluto might need a cold start to capture Charon, the interesting thing is that Pluto and Charon both sustain additional heating during and after the impact. So what I'm showing on the left is a temperature plot of Pluto and Charon, kind of a cross section similar to the video that I showed you. On the right is temperature with time from impact, and red is Pluto's core, the center of Pluto's core. Green is Charon's core, the center of Charon's core, and then the core mantle boundary inside Pluto is yellow. And I've tried to make that easier to understand with these dots, but it may or may not work. What's interesting here is that obviously nothing happens inside Pluto's core. That's not necessarily surprising, but the entirety of Charon experiences a temperature jump of at least 20 Kelvin, whereas the core mantle boundary of Pluto experiences around an 80 Kelvin jump on average. That can drive you from, if your basal temperature is 200 Kelvin to above the melting point. So the impact itself could enable the ice shell in both bodies to transition from marginally subsolidus to partially molten. So this could be how, if you start cold, you get an ocean. Whether you can keep it is a different story. I will skip that for time. The other interesting thing is that kiss and capture can feasibly reproduce the smaller Orcus and Vanth system as well. Because we were thinking about, okay, Pluto and Charon operate within a much larger framework of Kuiper Belt objects. Could this work for other bodies that are smaller? And it seems that it does, which means that the conditions that created Pluto and Charon could potentially also affect other large Kuiper Belt object binaries, though that's the subject of future work. We can also reproduce Eris and Dysnomia, but all I have here for you today is Orcus and Vanth. What happens is relatively similar. So the two bodies collide and then gradually separate and establish independence. Though in this case, Vanth is very football shaped, so that's a little concerning. I should say that the reason we selected Orcus and Vanth is because they're similar to Pluto and Charon in that they have a similar mass ratio between the primary and the secondary. So they're effectively a 40% the size, 40% the mass Pluto and Charon system. So it made it easy for us to test. Being able to show that we can both reproduce Pluto and Charon and a much smaller system shows that this may be pretty promising, though the caveat that I will say here is because Orcus and Vanth are so much smaller than Pluto and Charon in real life, they probably contain some amount of porosity, which is something that we cannot currently incorporate and would change these results somewhat. So I cannot fully say that this would work for much smaller bodies without incorporating additional, more realistic ways of approximating rock and ice deformation, but this is at least a start to doing that. Now, the key points that I would like to leave you with are first, that in the Kuiper Belt where velocities are relatively slow and sizes are relatively small, material strength changes how Pluto captures Charon, and it does so drastically. And the main takeaways from how it changes things are that it keeps Pluto and Charon largely intact. The Charon that you start out with at the start of the impact is the Charon that you end up with, and same with Pluto. And it then releases a satellite on a close, low eccentricity orbit that then stabilizes very quickly and presumably circularizes very quickly as it migrates outwards. These changes to the mechanics of how impact-driven satellite capture work have geologic implications for the evolution of Pluto, Charon, and other large mass Kuiper Belt object binaries. Thank you.
Thanks. You always showed Pluto and Charon already differentiated.
Yes.
How essential is that?
Probably somewhat essential. One of the things that's notable here is in these simulations, we don't try an undifferentiated Pluto and Charon. The reason why we don't do that is because it's very difficult to realistically make a strength model for a mixed rock-ice body. it's difficult to trust, because at that point you have to say, okay, we can guess that the weaker material, which is ice, would dominate. But at that point, you then have to guess how much does it dominate and why. So I don't feel comfortable making an undifferentiated body where I then have to kind of make the strength model myself and guess at the behaviors. And this is just because there hasn't been that much laboratory work looking at rock ice mixtures under these conditions. I'm working on doing that, but does it matter? It probably actually matters a lot, because what we think happens during impact is that right at the initial impact, when temperatures and pressures are the highest, the ice will dominate, but then as pressures and temperatures start to die down, but you still have deformation, the rock component will start to dominate. So that will probably change this result in some way that I genuinely would not feel comfortable fully speculating on. I think it would still work, but we're working right now on getting a mixed rock ice strength model that we can actually feel comfortable about testing. So this is the subject of future work.
Brian Holler, Space Telescope Science Institute. You in the model look like the debris disk, which presumably forms the minor satellites later, was mostly from Charon.
Yes.
Is that true in all of your simulations? Are you mostly
Yes.
getting exclusively material from Charon and very little, if anything, from Pluto?
Yes, Pluto loses very little of its material, and if the moons form from that debris disk, they're going to form primarily from Charon-based ice. Yeah.
Wonderful stuff. I have two questions. One is, can you make Kamehameha? In other words, that's something that failed, and explains what that is. And the second question is related to the question you just had. How much stuff is left in the debris disk? What happens to that? And one little question I've always wondered is, where did the Sputnik Planitia impactor come from? And I'm wondering if that was something that was sort of made on the site up there that eventually found its way in. So,
Okay. I think that's 3 questions. I'm going to try to keep track of them.
well,
Oh, they're all very great. Let me think. So,
Kamehameha and Sputnik, that's two.
can I make Haumea?
Yeah, can you make Kamehameha?
Haumea is a difficult system to attempt to reproduce, because not only does it have 2 moons and a ring, it also has a collisional family. So this is something that we are working on, and I'm writing a proposal to try to get funding to do that. But it's a lot more complicated of a system. So maybe. When I said I can produce Eris and Dysnomia and Orcus and Vanth, I said that because those were the easy ones to do. So yeah, I'm trying. I'm having some difficulties. It's going great. Okay. What happens to the rest of the debris, and could that debris produce the impactor that then makes Sputnik Planitia, is the second question. Well, it's hard to say, because what I've shown you here is the impact and then up to 60 hours after
Yeah,
the impact. We can't track the evolution of the debris over time, and the reason for that is because SPH is designed to handle the timescales of impacts and not geologic timescales. So I would love to work with people on the evolution of the debris. I've done some initial analysis in Rebound to try to determine how much of the debris is bound to the system and whether some of it will recollide with the system, that kind of stuff. And what I found is there's enough mass in the debris disk to make the moons. There is not enough mass to make the Sputnik Planitia impactor, depending on how big you think it is. Depending on the models that you look at, from some of the ones that I did several years ago to the ones that were done in the Splatnik case, which needed a much bigger impactor, you need a body the size of Mimas or larger to collide with Pluto to produce Sputnik. And the reason you need such a large body is because the collisional velocities are so low. So we're not building Mimas out there in the debris disk, which means we need an independent body.
Hey, Steve Dush. So I want to time when the event took place. If it took place at around 6 or 7 million years, I'd be really happy. So we can't have an ocean. I get that. But how early can we constrain? What's the lower limit? Based on whether the bodies need to be differentiated and have rock mantles, or ice mantles and rock cores, or can they be undifferentiated?
Well, as I mentioned, we currently can't reliably test an undifferentiated impactor or target right now. The reason that Robin was able to do that is because she's not using strength models, so she doesn't if they're both deforming like fluids, then you don't really need to worry what the rock and ice are doing because they're doing fluids. So currently, I'm assuming that both bodies are fully differentiated. If they are partially differentiated and you have the carapace, this may still work. What we're finding in terms of what happens is that the initial collision is the most important thing. And what's most important is if Karen collides with Pluto, does Pluto successfully resist deformation enough that Karen only gets partially stuck to Pluto for a little bit and then pushed back off? Presumably an undifferentiated carapace would also provide sufficient resistance because it does the rock ice deformation thing that I mentioned earlier, and this would probably still work. What I really can't comment on is a fully undifferentiated body.
Thanks.
I wish I could give you more certainty.
We have an online question from Larry Trafton. What if the impact angle were negative, i.e. if Pluto were spinning oppositely during the collision?
Yes, this is not something that we tested. This is something that Rob McKinnon and other people have looked at for the moon, and this would be kind of an off-axis impact. So what we're assuming here is that that Karen collides with Pluto and Pluto is spinning prograde relative to the impact. If Pluto is spinning retrograde relative to the impact, you then lose some amount of energy during the impact. What Robin found in her analysis of what this looks like for the moon, if you have this offset between the spin axis and the collision site, is that you end up needing slight variations in impact velocity or impact angle to then reproduce the system, but it did not nullify her results. While this isn't something that I have tested for Pluto and Karen, I do think that a similar result would be what I would get, which is that we would probably have to tweak things. We may have to collide Pluto with Karen slightly faster or at a slightly different angle, but this process would still operate.
Oh, okay, well, I'll have a question. Yeah, just to follow up on one of just the comment, it's very interesting that the stuff from the backside of Sharon becomes the disk, because if you think that the icy, Nix, Hydra, and Kerbos and Styx are all icy, then it's telling us that Proto Sharon had ice on the outside at that time. That was at least partially differentiated. So that's a cool implication. I'm just going to ask about the super Arakoth.
Oh,
because I realize it's only 60 hours, but
Yeah.
If you actually take the angular momentum of Pluto Sharon, you can't make a single body
yes.
stably. So I assume it's going to fission at some point.
I assume it would fission at some point, yes. Yeah, if you combine the mass of Pluto and Karen into a single body, it should split apart. So it would spin fast enough that it should split apart. So theoretically, yeah, the super Arakoth is probably not stable. It was just stable on collisional timescales. So we could not split it apart, even if we ran it out to 100 to 150 hours, which is the most that I would trust running one of these models too. So
Yeah, so I'm just wondering whether we can really say that an ocean-bearing system can't ultimately get to where we need to be. Well,
yeah, that is it.
I'm not complaining.
Yeah, that is a fair comment. I think what we can say then is that if the system is ocean-bearing prior to collision, then the collision itself is slightly more transformative because you end up exchanging a lot more material between Pluto and Karen because they are literally stuck together for potentially geologically relevant
Yeah, the
time.
cores have to merge. They
Yeah.
have to fuse.
Yeah,
Okay.
the cores get stuck together for a little bit, and that itself is interesting. If they're both ocean-bearing and then they merge to that degree, that is potentially very geologically interesting.